So I will turn it over to J. Rob as he's affectionately known. Oh, yeah, of course.
We might want to find a place. All right. Cool. Sweet. Well, I'm really glad that no one here is an expert in radio astronomy, because that means I can make up anything and you'll believe me. So, my name is Justin. I'm a first-year grad student at GSU, and my expertise, the stuff that I've done most research in, is radio astronomy. So I'll tell you how we get information from the galaxies that we want to look at through the radio spectrum, namely distances and velocities. So, no? No? Okay. All right. So, I didn't know about radio anything either. So, among all of the other stuff that galaxies emit, optical light normally, ultraviolet, all that stuff, it turns out that galaxies are huge sources of radio waves. So, that one, a bunch of other ones. And just so we're on the same page, just where radio is on the electromagnetic spectrum, you've got the really high frequencies, really short wave stuff near gammas, near X-rays. You go over to the visible light, the stuff that our eyes are attuned to. You still get some pretty high frequencies and pretty short wavelengths. Now, if you go all the way to the left, really long wavelengths, really low frequencies, that's where my stuff operates. So the question is, what makes galaxies emit radio waves? Why can we see it in the radio spectrum? It turns out that it's got something to do with the really cold neutral hydrogen. I don't look at all the excited, burnt stuff that Jay and Mitch do. I want to look at the boring hydrogen. That stuff tells us, does it not show? Oh, there it is. You can't really see it, sorry. That says cold neutral hydrogen undergoes an energy transition known as spin flip. All right. Spin flip sounds kind of scary and kind of complicated. That's because it is. So I'm not really going to go into it because I don't really understand the really nitty-gritty quantum mechanics. I'm an astronomer. That's not what I pay attention to. So the basic thing you need to know is that in a neutral hydrogen atom, just one proton, one electron, these particles have an energy associated with them called spin. Just think of it as spin energy in a specific direction. Now, there's a certain probability, very low probability, but there is one, that the electron will go ahead and flip its spin. When it does that, it enters into a lower energy state. And once that happens, that leftover energy needs to be accounted for, and it is. It's emitted in the form of a photon. So I said that there's a very low probability of this happening, so why do I care about it? This happens so little of the time, but there's so much hydrogen in a galaxy that it looks like it's happening all over the place. So there's some hydrogen right there, right there, right there. There's probably some over there. So we get a really steady stream of this radiation coming from the cold hydrogen. So we build these huge radio telescopes. And yes, if anybody's got a keen eye, that is from GoldenEye. That is where Sean Bean died. Spoilers, sorry. sorry. It's Sean Bean. What were you expecting, him to live? So radio telescopes, this one's Arecibo. They're built to detect these photons that have a really, really broad wavelength, which happens to be 21 centimeters long. It's about that long-ish, really, really big, and a really low frequency of 1420 megahertz. Now, so I'll get into a little bit about the telescopes that I've been to and telescopes that I do. So Mitch mentioned the Hard Labor Creek Observatory that has a 3.5 telescope. It's a pretty big telescope. That's cute. It ain't got nothing on my telescopes. Okay? Arecibo is 305 meters long. It's about 1,000 feet. It was the biggest telescope in the world until China beat us. I'm not bitter about that at all. That one's about 500 meters long, so it used to be the biggest one. That one's located in Puerto Rico. The telescope's fine. It got hit by some storms recently, but it's okay. It's fine. It's still going. The other one I've been to is the Green Bank Radio Telescope. That one is 100 meters long. That one does hold a record. It's the world's largest fully steerable telescope. That thing rotates, and that thing bends completely, so it can see a really large portion of the sky no matter where our Earth is in orientation to the sky. So those are two telescopes that I've worked with. This is what a hydrogen detection, cold hydrogen detection, looks like. Now, these are what I've lovingly referred to as Batman detections. I have tried for years to get them to have that be the official term. I have not heard back from them. So, if I saw this for the first time, I'd have a couple of questions. Namely, why are there two horns? Why does it look like Batman? Not just the fact that it's cool. Why does it look like that? Why isn't the spike centered at 1420 megahertz? You see that the center of this thing is at about 1417? Why would I lie to you? We're all friends here. And why is it fat? So, let me get into why all this stuff goes on. So, if I'm telling you that all of this radiation that we're detecting with these radio telescopes comes from hydrogen, where is that hydrogen located? Well, in order for this specific spin flip stuff to happen, the hydrogen needs to be cold and needs to be neutral. Where is cold, neutral, calm stuff hanging out? It's hanging out on the outskirts of the galaxy, where everything's calm, stuff's not moving very fast. You get in closer to the center of a galaxy, things start moving really rapidly, temperatures heat up. That's not the stuff I care about. So, if we were to detect a galaxy like this, like NGC 4151, face on, it would look kind of boring. It would just look like a normal Gaussian or a bell curve, if you know what Gaussian is. It would look pretty boring. That's because it's face on. So we're getting a really symmetric detection from all the hydrogen around here. If we look at edge-on galaxies like NGC 5907, then we get into some real stuff. That's where Batman happens, okay? We get hydrogen stuff from here, but we get most of it from the edges right here and right here because we're looking at it edge-on. Most of the stuff we're getting from in front and behind, so we get a larger flux from this hydrogen on the edges of the galaxy. So the part that blocked Jay's observations, what'd you call it, the torus? Yeah, my stuff blocks Jay's stuff. Sorry. So that explains the horns, but that's only part of it. I can explain all three questions with a concept that has kind of been gone over before, and that's redshift and blue shift. So, really quick metaphor so we're all on the same page. Think that you're standing on the sidewalk and you hear a car coming towards you. What does that car sound like? It sounds higher pitched. Why does it sound like that? As the car is coming towards you, it's emitting sound waves at a normal rate, but it's moving towards you at a specific rate, so all the sound waves get crunched up, the wavelengths get shorter, it sounds higher pitched. When it moves away from you, the opposite effect happens. The wavelengths are stretched out, it sounds at a lower pitch. Light behaves in the same way. So if an object's coming towards you at a specific velocity, the wavelengths are going to get shortened, it's going to look a little bluer, and if it's moving away from you, it's going to look a little redder. We see that happening on a galaxy. That's edge on. That's where that's why Batman doesn't just have horns. The horns are separated, so his head gets really fat. All right? If a galaxy is rotating like this, from our perspective, it looks like one side of the galaxy is moving away from you while the other side is moving towards you. So one edge, one of the horns is going to be blue shifted and one of the horns is going to be red shifted. So those two peaks are centered at two different frequencies. That's why it's fat. Did I get everything? Why isn't it centered at 1420 megahertz? Well, let's look back at N4051 here. Why isn't it centered at 1420? It's the same thing with redshift and blue shift. If it's shifted over lower than 1420, what does that mean for the entire galaxy? Is it moving towards us or is it moving away from us? Away, yeah. The entire thing is redshifted. And you can see the different spikes up here are centered at different frequencies because even though the entire galaxy is redshifted from us, even though the whole thing is moving away, some of the galaxy is moving more away and some of it is moving towards us. Okay, so what I've talked to you is how these detections tell us the orientation of the galaxy, the way it's rotating. The things that I promised you at the beginning were velocity and distance. I can cover velocity right now. It turns out that if we can measure redshift from the Batman horns, the more redshifted they are, right, the more shifted in frequency they're going to be. If they're more redshifted, they're going to go into lower frequencies. If it's more blue shifted, it's going to go into higher frequencies. If it's more redshifted and blue shifted, and because those have to do with velocities, that means the edges of the galaxy are moving faster if they're redshifted or blue shifted. That means that we can get a measure of how quickly the galaxy is rotating in general based on how fat these Batman detections are. If it's really fat, that means the galaxy is rotating really fast because there's a really dramatic change in redshift and blue shift. If it's really skinny, it's not moving that fast. And that leads into how we get distances from this stuff, and that has to do with something called the Tully-Fisher relation. Now, a couple of decades ago, two scientists, Tully and Fisher, they discovered that there's a correlation between how fast the galaxy is rotating and how luminous it is, how bright it appears in the sky relative to us. The other thing that they found out is if a galaxy is moving faster, that means it's bigger. Those things are just intimately correlated. The fatter the galaxy is, the faster it's rotating. What they also found out is the faster it's rotating, the more luminous it's going to be. So on this here, you have apparent magnitude, which is how bright it appears to us from our perspective. If you have a lower number magnitude, it means it's brighter. So this graph shows you the line of how fast it's moving and then how brighter it appears. And that also has to do with its distance from us. Something that's really dim is going to be really far away, and something that's really bright is going to be close to us. So the way we get distance is we compare the apparent magnitudes that we get from the Tully-Fisher relation that tells us how bright it appears to us, and we compare that with corrections of how bright it should be. And if we get a distinction of how bright it should be and how bright it is to us, we can get the distance from them to us. All right. So in my undergrad, I worked with the Arecibo Pisces-Perseus Supercluster Survey, which is basically a gigantic survey that has hundreds upon probably 300 or 400 undergrads, researchers, doctors, everybody from your uncle to whoever. They are looking at the biggest supercluster in the sky, which is the Pisces-Perseus supercluster. It's about 250 million light years from us. And they're getting distances to all these using the Tully-Fisher relation. And what I did in undergrad is not only did I do reductions of all these hydrogen stuff, and not only did I analyze it, but the other thing Tully-Fisher needs is luminosity. It needs brightness. So it used the Sloan Digital Sky Survey to get luminosities, and my job was to get the good hydrogen detections and then say, okay, which ones are good and which ones are bad. Can I click on these links? Let's hope so. Shift or Alt? It did something. No? Hey! Oh, you have Internet Explorer. That's okay. So, here's one of the good ones. Can you guys see this? Come on. Where's my cursor? There we go. All right, give me back Internet Explorer. Do I have to drag it to the left or the right? Hey, there we go. Okay, this is gonna be really weird. Okay, so this would be an example of a really good detection. You can see the galaxy. There's nothing in the way. There's no optical aberrations. There's nothing wrong with the equipment. It's fine. It's a great galaxy. So let me get it back here. Oh boy. I'm going to show you guys one of my favorite ones that I did. I called this one the Christmas Galaxy. The error has occurred with the Sky Server. That's cool. All right. Science. Go back. Oh my God. Is it back? Okay. All right. Just take my word. Yeah, everything has technical errors. This was the one that I was going to show you. This one's zoomed in. This would be an example of a bad optical image. This is stuff that we would have thrown out. Here, you see this little pixel here. That's where the galaxy is supposed to be, but there is a star in the foreground that is so much closer to us than we are to the galaxy that the brightness, the light from this star is completely drowning out the rest of the image, so we can't even get any luminosity from that galaxy that we were looking at. And then this next one happens to be my favorite. This is what we call the Squidward Galaxy. Yeah. Yeah. I think I put that on, I think I put that on one of the reduction pages that we were using for the survey, and I got an email back saying, is this supposed to be funny? I didn't respond at all. No. So, why do we care? Why do we want distances to all these galaxies? Why do we want to measure velocity? This image has already been shown. The reason why we want this is because these big surveys measure distances in order to get velocities, okay? So, or not just radial velocities that the H1 lines give us, but the velocities that have to do with the expansion of the universe, okay? So if we know how far something is away, because the expansion of the universe causes things that are farther away to be moving faster, if we get the distance, we not only know its radial velocity, but now we have an estimate as to how fast it's moving away from us. And we compare that to how galaxies are moving in these big superclusters. That's just one little piece of these giant web things that you see in the simulation. It's just one small piece of that giant thing. So when we compare velocities of things moving away from us to how they're infalling into these big superclusters, we get an idea as to how these huge things behave in the universe, how big clusters and big superclusters form. And based on that data, we get a better model and we get a better picture of what's actually happening out there. So what now? What am I doing now? Well, I am working with Dr. Misty Bentz. As of right now, I'm looking at H1 data from active galactic nuclei, which has already been described before. Stuff that's fallen into the black hole. If you've seen Interstellar, anybody seen Interstellar here? Great movie. Yeah, you're all friends now. That's the best representation of what an accretion disk would look like. Stuff falling into it, gas, dust, Matthew McConaughey, all the stuff like that. And what I'm doing right now is I'm looking at about 30 targets of AGN. I'm reducing and analyzing all the H1 data stuff. Eventually, I'm going to move away from radio, sadly. I'm going to move into the pretty pictures, the optical stuff. It's boring. I don't like it, but it's fine. So what I'm going to do is I'm going to get all the H1 data from these AGN and eventually get distances, get Tully-Fisher distances, all this stuff, in an attempt to measure the supermassive black hole at the center of all these AGN stuff. If we have all the hydrogen data and we have a good idea of what the distance is, all that stuff goes into modeling the galaxy, subtracting all the hydrogen stuff that we don't care about anymore here, to get a mass as to what that bulge is in the center. And that's the big picture. And that's it. I have not. I just started there exists a catalog of black hole masses of AGN. Yes. So these will be either corrections, getting better masses, or there's a couple of new targets that I'm working with, so hopefully we'll put in some more masses there. Yeah, this goes into reverberation mapping. Yeah. Yeah. No, for that, I don't remember what the hydrogen spectrum looked like for that. Usually radio doesn't care about what's in the way. It just barrels through everything. That's why radio telescopes don't really care about clouds or whether it's daytime or nighttime. It doesn't matter. I'm assuming there was some effects. We probably got less of a flux because there was a bunch of absorption from that. Other than that, I don't know. It didn't matter anyway because we can get H1 stuff all day long, but in order to get distances, we need luminosity. So if we can't get any luminosity information, we're just making cool Batman pictures. Yeah. For AGN, I'm not sure yet. They're a lot closer than what I used to be working with. So all the stuff in the Pisces Perseus supercluster was hundreds of millions of light years away. This stuff is a lot closer. We don't get fluxes that are this big from stuff that's far away, and 4051 is pretty close. I don't know the distance off the top of my head. I think it's 13 megaparsecs. It just clicked, so something went off.